So now let's consider three types of algorithms for machine learning and what the differences between these three, if you like, fundamental approaches are. So first of all, imagine that we've got some data. We have a sequence, let's say, of sensory inputs coming from some kind of measurement in terms of vectors, so x1, x2, x3, and up to xn. Let's now think of three cases where we might only have that information, we might have more information, or we have to learn something else anyway. So let's think about the supervised learning condition. In that case, as well as having this sequence of inputs, we've also got a sequence of outputs corresponding to each of the inputs. So if you like, we've got an input vector, and we've also got, it could be the label, it could be the class of that input, it could be a value that we want to map it to. Now we call this supervised because when we're actually learning how to do this, we've actually got a data set of the inputs and we know what the output should be, and we can use this relationship in order to actually get the system to learn to map on the training data what the inputs are towards what the outputs should be. And then if we've trained it in this way, later on we can just give it the inputs and it should automatically tell us what the outputs are. However, in an unsupervised learning approach, basically this sequence of inputs is all we've got. We haven't got any other information about the problem. All we've got is the input data. And the idea is that our algorithm then should try to build up some relationship or make some sort of prediction or some kind of latent estimation of what's going on in the data. Can it say something about what the data is actually like? Can it cluster things together? Are some inputs close to each other and some farther away? So this is completely unsupervised. All we've got is the data, and the system has to work out something about the data itself. Now another class of algorithms are called reinforcement learning algorithms. So in this particular case, it's a bit questionable as whether or not we've even got the sensory input sequence in that way anyway. So what actually generally we've got is we've got an agent, and an agent is something which can take actions, and it's got to learn to make actions, and the only way it can learn to make actions is by trying them and then seeing what reaction it gets from its environment. Does it get a reward or a punishment? So reinforcement learning is quite different in many respects to supervised and unsupervised, because what we're doing is we're taking an action and then because of the action we're getting a consequent feedback of reward which can tell us whether or not that was good or bad. And also it might also be that we're also getting some estimate of what state we're in from the environment as well. So it's a different class of algorithm. So just basically to think of that in terms of a set of graphs, because we'll be looking at neural networks quite a lot from this. In the supervised learning case then, we've got the inputs or the observations of data, and we want to map them to the outputs which we have in the data, right? So we've got the input data and we also know what the outputs are. And we'll come across lots of examples of this in a second. It could be that we're mapping images to what digit they represent or something like that, but we've got that, the data's all labelled. In the unsupervised condition, what we have is we've got the observations, which are effectively the inputs, and that's all we've got. But somehow, can we actually learn a hidden representation which explains something about these? It could be just, like I said, it could just try to be clustering things together, or it could be coming up with a compressed representation which can also regenerate the observations of the data. But the important thing is, we've just got the data and we don't know anything about it, and it's got to work out for itself in unsupervised learning. So let's think a bit more about supervised learning. A classical example would be a classification task, right? So we've got a set of inputs and we've got a discrete set of outputs. So discrete is the important word here. To classify things, you classify them into a discrete set of outputs. And a good example of this is something like character recognition. So imagine we've got images coming in from a camera, And we probably built up this data set. You can actually download them. For each particular picture, if you like, of a particular character, we are also told what the character is. So we get some very, very pixelated image in this case for an A, pixelated image for a B, and for a C. But we're told this is an A, we're told this is a B, and we're told this is a C. So there's 3 different classes in this case. And in this particular case, all we have to do is then, on the basis of this little image, we have to say, in this case, if it's an A, a B, or a C, in a digit recognition task, for example, we would have to say, what does this image represent? In this case, it's going to be a 7. This one would represent a 5. This would represent a 3. And again, that's the idea with supervised learning. Specifically for classification, you've got a discrete number of outputs. The important thing is we've got the input and we know what the output is on the training data. So there's another supervised condition though, which doesn't actually use classes at the output, that doesn't use these discrete values. So in a classical image recognition of digits, let's say we've got a picture and it's got to represent the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's got to represent these 10, if you like, discrete things. Now in regression, we don't have discrete outputs. We've got a continuous value. An example of regression might be, for example, that we're given the weight. Let's say we've got a data that's giving the weight of a baby, and the output is going to be the height of the baby, say, right? And this data set is actually going to be very well. If you've got enough points on this, this is going to be spread across lots of values. It could be a floating point value on a computer. And the output also that it corresponds to, the corresponding height, is also going to be a floating point value. So it's not an integer. It's not breaking these things down into, short, medium, tall. That would be an example of classification. It's actually mapping one, in this case, continuous value, which is weight, to another continuous value in which is going to be height. Right? And there's lots of examples where we do have this regression task where we're actually mapping to continuous things rather than mapping to discrete things. In unsupervised learning, basically we're trying to find some structure in the data, and a good example of that would be clustering. Now here's a 2-dimensional data set. I'm plotting feature 1 on the x-axis and feature 2 on what's normally the y-axis. And as you can see, just looking at this data, if we don't know anything about it at all, we can plot it like that, and we can immediately see, because we're very good visually at actually looking for structure in things. We can see as people, yes, it looks like there's 4 distinct things here. There's a cluster here, there's a cluster here, a cluster here, and a cluster there. So what we're looking at is saying, look, all the points within a given cluster seem to be grouping together, right? And then there's a bit of a gap between the clusters, and again then you've got another cluster where everything seems to be grouping together. Now we can actually find these clusters automatically using some machine learning techniques. These are unsupervised techniques. They're just looking at the data, just on the basis of looking how far data points are away from each other, and then assigning ones which are all close together to a specific cluster. And that's exactly what this example is showing here. What we've done is, this is probably using something like a k-means algorithm, but basically what it's saying is all of these data points here, they represent one class or one cluster. These ones on the left represent another one. Again, the red ones down here represent another cluster, and the blue ones here represent another cluster. And we can just basically analyze the data without knowing anything about the structure and come up with this mapping to these 4, if you like, discrete clusters, which we could consider as being 4 different classes. So another useful thing about unsupervised techniques is that we can also say something about the dimensionality of the data and how relevant it is along certain dimensions compared to other dimensions. Now, if I've plotted something out like I have here, I've plotted one-dimensional data, one dimension of the data against the second. What we see in this particular data set is a lot of it is kind of along this main leading diagonal here. right? So there's a lot of spread along here, and there's not as much spread orthogonally to that. Now what we can do if we have this kind of data set, a more effective representation of this data set would be to say, well, rather than using feature 1 and feature 2 along these axes, what about if we use this axis here, this leading diagonal, as being one of our dimensions, and then the orthogonal one to it being a second dimension? And that is exactly what principal component analysis will do. You can analyse the data, and what it'll do is it'll give you a new set of orthogonal axes, which basically start with principal component 1, 2, 3, 3, and whatever, up to know how many dimensions you've got. And the first dimension will capture the most variability in the data. The second one, the second most. In this case, there's only 2, right? So we capture most of it with the first dimension, and then not as much with the second. Now, actually looking at that, what we can say is actually that the data shows a lot of correlation, because what it's saying is as I move along the x-axis, I also move along the y-axis. Now imagine I'd got a set of data such that the x value and the y value were exactly the same. What would that look like when we plot it out? So what it would mean is if I had -4 here, I'd have -4 here. If I had 2 here, I'd have 2 here. So what we'd find in that case is all the data was on a line angled at 45 degrees. And in that case, our representation would be completely redundant, because it's basically got, well, not completely redundant, it would be redundant in one dimension, because the x-axis would say everything we needed to know about the data. And then when we actually represent it in this way, the first principal component is all that you would need to represent the data. Another thing you can do with unsupervised learning, again, like I said, is to find a representation of the data in terms of maybe a simpler set of parameters which can explain the observations. So it could be that we've got this data coming in at the bottom here, but we can represent it, and this is probably not a very good drawing because we've got the same number of nodes here as here. Imagine we only had 2 nodes here. It could be that we can use just 2 nodes to explain all the data, and we can find these things automatically just looking at the data. Another thing we can do with unsupervised learning is another form of clustering, actually, when we're actually looking at things in terms of probability distribution. So we can actually capture things about the data in terms of representing in terms of probability distribution. In this particular case, the data here, we'll see in a second, but looks sort of kind of Gaussian, in like a one-dimensional Gaussian effect. So we can, in this particular example, we're sort of seeing that this red curve is a reasonable fit for the data set cluster here, and the second blue curve here is a good fit for the second lot here. So in this case, we could represent this data using an unsupervised algorithm, which makes use of, in this case, it's actually going to be a mixture of Gaussian's model, by saying that, you know, we're going to model the data in terms of 2 distributions, and then which distribution is the most likely one for any data point, and then we can associate it with each data point in that way. So the fact that we can actually sometimes build representations from data which use this sort of latent representation, which might be less in terms of the number of parameters it needs than the original data to represent the data, means that sometimes we can use it for compression techniques, and certainly this is a technique that is used. Principal component analysis also will you know, we can get rid of redundancy in the signal, and if we can get rid of redundancy, that means we don't have to transmit everything twice, say. So these things can be useful for compressing, and then of course we need to decompress, so encoding. Outlier detection is another useful aspect of unsupervised techniques. So basically what we're saying is, you know, imagine looking at something, a picture like that, and we with our visual systems can immediately see, well, there's the odd one out here is the red apple, right? Now if we represent, in this case, let's say we represent information regarding an image of a particular apple, in this case with 2 dimensions, this is just this is not necessarily related to that, but imagine we've got that kind of thing happening. What we see in this particular data set is it's kind of everything's kind of in the middle here. So it could be that, what shade of green is it, and how, what shade of, or how heavy it is, or something like that. And you'd expect apples, for example, to be sort of within a sort of a cluster, if you like. Now, if someone put a melon into the machine by accident, then it will have greatly different properties. So it would be a long way away from the, if you like, the normal centre of where everything normally is. And because of that, using this kind of techniques, we can immediately say, if we've got this kind of representation, if we end up with a data point which is way away from where we normally get them, something's not right. And this could be because we've got the wrong colour apple, right, in this case, or it could be that there's a lot of noise in that measurement. And this sort of detection of things which don't fit into the norm, if you like, is sort of called outlier detection, and it can be very useful for quality control amongst everything else. Unsupervised classification, well, we can also because it basically maps like to like and compares, or if you like, puts things that are very similar into the same cluster. We can also use it to automatically recognize stuff in the environment, like the sea, right? The sea is this sort of blue thing here, and that's different than some of the mountains up here. There's also some water here. So if we run a simple clustering algorithm on that, we may well come up with a map which looks like this. And you can see now it's labelled all of the sea, nice blue colour. It's also showing the lake here is probably also the similar kind of thing than the sea. So in this case it would be, because it's got water in it. It could maybe even that there's some water coming down here, I don't know. But what you see is just on the basis of self-similarity in this case, or defining a sort of similarity metric, it's possible to, in an unsupervised way, immediately say something about the data that you didn't know anything about to start with, but just, on the basis of the data only and nothing else, you can do some useful labelling in this case. So reinforcement learning, right, that's, like I said before, is about getting an agent, and an agent is kind of like a person is also kind of an agent to make decisions and to take actions given it's in a certain situation. And in order to learn, it's got to interact with the environment, right? So it's got to, if you're in a maze and you want to find the way out, you've got to move left, right, up, down, and see whether or not finally that path goes all the way to the way out of the maze. So you've got to interact, do something, experience something coming back, and then on the basis of that you can finally work your way out as being work out what to do. So there's no supervisor in reinforcement learning. The agent's just doing things on its own. All it gets at some stage is reward, right? So again, if you're in a maze, you might have to wander around quite a long time before you find the way out. But hopefully when you do find the way out, you can kind of remember enough about how you got there. So if you got put back at where you were before, you'd actually be able to get out again. And it's the same kind of thing with reinforcement learning. It's kind of associating the state that you're in at any particular point in the maze with, which way you should be going from there to get out or get your reward. And it's done initially by trial and error, right? So if you don't know anything about what you're doing, you've got no alternative than to effectively randomly choose one of the actions you can perform. Now, as you learn a bit more, you can basically say, well, I have a sort of a feeling or a belief that doing this is actually better than that. So within this framework of reinforcement learning, what we do is we define states, because we want a nice clean representation, a set of actions, a transition function, and what the transition function is given the state we're in and given an action, where do we end up? What state do we end up with? So we transition from the state we're in to another state. And the reward function. So the reward function tells us if we're in a given state and we take a certain action, what reward do we get for that, right? And typically with mazes, you only get a reward when you actually get out of the maze or you get to the goal. And you'll see quite often it drawn in this schematic. You've got your agent at the top. The agent, first of all, can sense the environment. It gets two things from the environment. It's going to be in a certain state to start with, so it can see the state it's in, or it can maybe sometimes it has to estimate the state it's in. It can see whether or not it's getting reward from the current state. And then it can take an action. In fact, that's all it can do. It can take an action, right? And then this affects the relationship of the agent with the environment. Because you've taken an action, you change the state you're in, unless you're unless you're walking against a wall, in which case you come back to where you were. But basically, you take an action. If I go left, I've gone a little bit to the left, and if I'm in a room, I've gone maybe closer to the wall. And did we get any reward from doing that? If you're standing next to the to the way out, and then you move in that direction, and then all of a sudden you are out, that could constitute a reward. So the agent then gets this updated reward and the updated state on the basis of the action, and it carries on like this until basically it can get to the final goal, and then you might want to run it again, and basically you just learn and learn and learn how to associate what the state is with the action that you need to do there. So the agent has got to learn what to do, right? What action to take in a given state, and all it gets back is the reward from the environment. It might also get some signal back telling it about the state. In the first few examples, we're going to be explicitly telling you what state you're in when you get the next state. Sometimes you don't get that information. Sometimes you've got to estimate the state as well. A very famous example of reinforcement learning now is the one that was used by Google DeepMind to learn to play Atari games, right? So what they did, this is very good. It was basically, how did you play Space Invaders? And the nice thing about this algorithm is that all they gave it as an input was a downscaled or a downsampled image of what you'd see on the screen. So it's watching, obviously not with its eyes because it hasn't got eyes, but it's basically getting this picture every so many milliseconds, and it's using that to estimate what state it is in. And all it does is it does some complicated processing, in fact using some deep neural networks, in order to say the state is determined by what I'm seeing now. I want to generate an action, right? And I want to generate an action such that I can get a better reward or get a long-term reward. And the system is also given a score as well, right? So all it's got to do is look at the picture, the image, every so many milliseconds. At every step in time, it then tries to work out how to move the joystick. Does it move it up, down, left, right? In fact, one of 18 joystick actions is something it had to learn to do. And all it gets is the picture, and it gets the score that's running. And they ran this for a very long time in order to train it. And the really nice thing was they managed to get this algorithm to work better on the game of Space Invaders than a human has ever done, right? So it achieved superhuman performance, and it's kind of using a kind of almost naturalistic image kind of input, rather than being in a very artificial, if you like, setup that we do with mazes quite a lot.